This is the final project demo for IT forensics. We're going to be going over deleted file recovery on the FAT32 file system using some very simple commands on Kali Linux, as well as an understanding of the FAT32 file system. So to begin, we have an image of a storage device, and we're going to take a look at the partitions on that device using the mmls command. So our image is the thumb image fat.dd file. We can see here that we have a FAT32 partition here at sector 97, and we're going to want to extract that partition. So we'll use the dcfldd command. IF, or input file, will be the thumb image fat.dd. Out file we'll just call fat partition. Block size is 512. That's the units here that we're looking at. Count is going to be equal to the length, so that's 24, or 248,000 rather, 223. And skip is 97 because we start at sector 97. So this is going to extract just this FAT32 partition that we have there. So now that we've extracted that partition, we're going to take a look at it using fstat, just to take another look at the file system and get some information that we're going to need to recover the deleted files. So fstat minus f fat, which is the file system type here that we're specifying, minus b 512 is the block size. So we saw that in the previous output of mmls, it's 512 byte sectors, and fat partition is just our input file that we're taking a look at here. So we can confirm the file system type is FAT32. Some other information we're going to need here is the root directory area, so that's going to be sectors 8192 to 8193. Root directory is going to have entries for our deleted files, and we're going to need to take a look at those entries to figure out where exactly those are located so we can recover them. Another thing we're going to need to look at here is the data area. We're going to need to know where the data area is because we need to extract the data area to extract the deleted files. And the last thing that we'll need here is the cluster size of 1024 bytes. Now that we know where the root directory is, we're going to go ahead and use dcfldd to extract it from the partition. So dcfldd in file is going to be our fat_partition. Block size is 512 because we're still working with sectors, the 512 byte sectors. Count is going to be 1 because the root directory is only one sector long. We're going to skip to sector 8192 because that's the starting area of the root directory. We get that information here. And then the out file, we're just going to call it fat root directory. Next, we're going to take a look at the contents of our root directory using hex dump. So we're just going to use hd fat root dir. Okay, so some things we can gather from our root directory by looking at these entries. We know that each entry is going to be 32 bytes. So this is a block of 32 bytes right here. The important thing we need to note is by looking at this 11th byte, we can see the type of entry. It's an attribute, and this attribute of 0f indicates that this is actually a long file name entry. The way long file name entries work is that FAT32 root directory entries only support up to 11 characters in a file name. And if they're more than 11 characters, then a long file name entry is going to precede the entry of the actual file. So in this case, we can see the file name stored in the long file name entry is sus_file.txt. So that's what this first entry is for. The next entry then is going to be the actual file entry for that susfile.txt. What we can gather from this is the first byte is going to show us whether or not the file is allocated, or it's going to show us the first character of the file name if it is allocated. In this case, E5 means it's unallocated, so someone's deleted this file. Next, we want to look at bytes 20 and 21, which are right here. These are the high 2 bytes of the first cluster address. They're just 0000. And then bytes 26 and 27, which are right here, are going to show us the low 2 bytes of that cluster address. So that's 000D. Keep in mind, this is little endian, so this is actually the start of the byte, and this is the end of the byte. So 000D. So we'll keep that noted for later on. We're going to need the cluster address when we extract the file. Finally, bytes 28 to 31 are going to show us the size of the file in bytes. So the file size here is 00003511, and that's in hex. So later on we'll convert that to get the actual file size in bytes. The next entry is another long file name entry. We can see that here with the 11th byte. So we'll just skip to the actual file entry for it. We can see that it starts here. It's unallocated. The file size is 0000. Sorry, the first cluster address, the high 2 bytes is 0000. The low 2 bytes of the cluster address is 001B, and then the file size is 00010B A3, and that's again in hex. We're going to save that for later when we extract the file. So our next step, now that we have that information about the unallocated files, is to actually extract the data area so that we can work inside of the data area using clusters instead of sectors. So to do that, we are going to use DCFLDD again, using some of the information that we have from FSStat, which is still just above us on the screen here. So DCFLDD in file is going to be the FAT partition. Block size in this case is still going to be the 512 byte sectors. Count is going to be 240,030. That's something that I've calculated using this value here. So 8,192 is our starting sector, and our ending sector is 248,222. If you subtract them, then you get that number that I put in there. And we're going to skip to that starting sector of 8,192. Our out file is going to be the FAT data area. So that's our data area extracted. And what we're going to do now is actually extract the two files using the information that we have from this hex dump here to recover them. So using the information that we got from the root directory entries for these files, we're going to extract them now. The first thing to note when we're extracting from this data area is that we actually start at cluster 2. So the data area starts at cluster 2 instead of cluster 0, so that's going to affect the skip value that we use for DCFLDD. So when we start by extracting the text file that we have, we'll use DCFLDD. In file is going to be our FAT data area. Block size this time is going to be 1024 because we're working with the 1024 byte clusters. Skip is going to be equal to 11. So if we convert the value of the cluster address to hex, we get cluster 13 as the starting cluster. However, since we begin with cluster 2 as opposed to cluster 1 or cluster 0, we actually need to skip 11. 2 plus 11 is 13, so that'll bring us to the 13th cluster. When we look at the file size of the file, which is right here, if we convert that from hex to decimal, we get a file size of 13,585 bytes. We divide that by 1024 for the bytes in a cluster, and we get a total of 14 clusters. So the count is going to be equal to 14, and the output will be the sus file recovered.txt. And we'll go ahead and do that, and we can do the exact same thing for our image. So FAT data area block size is 1024. Skip in this case is going to be 25. So if we calculate the starting address, we get cluster 27. So our skip is going to be 25 because our starting cluster is cluster 2. Count in this case is going to be 67 clusters because the file size is 68,515 bytes. If we convert that to clusters, it's 67 clusters. And our out file is going to be sus image covered.jpg. Finally, we can go ahead and open up the image file. We'll do xdg-open sus image recovered.jpg. And there we go. That looks like an image to me. I can confirm that is the image that was deleted from the partition. And finally, we'll cat out the susfile.txt, and we get, looks like a Wikipedia entry for Smiling Friends with this file is suspect at the top. So that is the process for recovering deleted files from FAT32 partitions.